indeed. 88% of you chose B, 2 times 10 to the 8th meters per second. That's 3 divided by 1.5 is 2 times 10 to the 8th. Perfect. So now we use what's called Snell's law to calculate the amount of bending of light at the surface, at the interface between two boundaries, between two materials. And we define the incident angle of our ray as theta 1. And theta 1 is measured from the ray to the normal direction, the direction perpendicular to the surface, which we'll take to be flat. And that's in a medium 1, which has index of refraction n1. And then the transmitted ray has an angle theta 2 with respect to the same direction inside the material. And you could think of this as air and this is water. And clearly the fact that this is bent like this indicates that n2 is greater than n1. We can see that from Snell's law, which just says that n1 times sine theta 1 is equal to n2 times sine theta 2. You could get that from that diagram where you match where the wave crests are arriving at the surface. You could derive this law yourself. We won't do that. We'll just use it. And you can see that if n1 is smaller than n2, then theta 1 is bigger than theta 2. They compensate each other. It's an inverse relationship. So that's why this angle is smaller if n2 is bigger than n1. Now we can demonstrate that with this little setup over here. Where we have a laser beam and some acrylic plastic, which has a fairly high index of refraction. When the beam hits the surface, it is certainly slowing down inside there. It actually has a different color inside there, different wavelength, right? But you can't see that because you can only see the light coming out, which is going through the air, not through the glass. Anyway, and then it goes straight through like that. Now what happens if I change the angle of incidence? You see that the beam inside is bent a little bit, and then when it emerges, because these two sides are parallel, the emerging beam is parallel to the initially incident beam. But now, even though I've turned this at like a 45-degree angle, you don't see the beam inside at a 45-degree angle. It's at a different angle, which you could calculate from Snell's law if you know the index of refraction of this material. Now, one interesting thing is it works in either direction, right? And that's kind of what you see here, that the beam going in is bent by a certain amount, and then it's unbent by the same amount when it comes out, because those two surfaces are parallel to each other. So it doesn't matter if the light is going into the medium or coming out of the medium. The path of the light is the same and follows the same law, Snell's law. Okay? So all I did to change this graphic is put the arrowheads on the other end of the red lines, because it works either way. So let's see if you really understand that. Imagine you're looking at a pond and there's a fish at the bottom of the pond there. You're standing on the edge of a pier or something. When you look, when the fish is down here, the light comes out, it hits the surface, and it gets bent like that and reaches your eye. So when you are looking at the fish appears to you to be over here. So objects are not where they appear when they are underwater. They're at least not in that direction. So if you wanted to take a spear and spear the fish, where should you shoot the spear? Well, you should always be shooting it below where you think the fish where you see the fish, because that's where the fish actually is. When the spear enters the water, it's not going to be refracted. It's not a beam of light. It's a big solid object, and if you want to hit the fish, then you have to send it in that direction, not where you see the fish. Fair enough. So let's see if you understand that. Suppose you're standing next to a pool of water, and you see a coin, and you have a laser beam, and you want to shoot the laser beam such that it hits the coin. Okay? Now you're looking down the axis of the laser. What should you do? Should you shoot it at the apparent position of the coin? Should you shoot it above the apparent position of the coin or below the apparent position of the coin? Discuss with each other